Here are solutions to homework set number 9 for ECE 111. Now this homework set you can do in MATLAB. I would recommend using a calculator. When you get to circuits 1, circuits 2, you're going to need a calculator that does complex numbers. My recommendation is the HP42. The 35S is the current calculator. They're currently selling for $300 on Amazon. Part of the chip shortage. There's a free app on your cell phone called Free42. This emulates the HP42 calculator, in my opinion, the best calculator ever built for electrical engineers. It's a little bit different. It's got a stack, so there is no equals button. To add numbers, I use the stack. So if I want to do 2 plus 3, say 2, enter 3, plus. With complex numbers, you've got this complex key. To do 4 plus J12, I do 4, enter 12, complex. And there's 4 plus J12. Kind of a sidelight, if we go under modes, there's also polar. I could do 4 at 45 degrees. That's one way. We're using rectangular. So starting over, 4, enter 12, complex, times 2 minus J13. 2, enter negative 13, complex, multiply, divided by 2 minus J. 2, enter 1, negative, complex, divide, and there's your answer, 71.2 plus J21.6. Second problem, same procedure. So we do 4, enter 12, complex, 2, enter negative 1, complex, take the ratio. Take the second number, 2, enter negative 13, complex, 2, enter 1, complex, take the ratio. Here's the result of the first operation, second one, add them. Now multiply, 3, enter 8, complex, times 9, enter 7, complex, divide, and there's your answer. So that's problem number 1. Problem 2 looks at adding resistors in series and parallel. In series, they add as R1 plus R2. That's series. In parallel, it's 1 over R1 plus 1 over R2 inverse. So to start out, I've got J400 in series with minus J800. Together, that gives you minus J400. In parallel with minus J700. Well, in parallel, the inverses add. So let's do 0, enter negative 400, complex. Take the inverse, 0, enter negative 700, complex. Take the inverse, inverses add, take the inverse. So all this together is minus J254. And this isn't necessary, but I'll show you how to store complex numbers. If I want to save that for later use, I can do store alpha A. I've now created a variable called A, where I can store stuff. That's in series with 300. In series, they add. In parallel with minus J600. In parallel, take the inverse. 0, enter negative 600, complex. There's the minus J600. Take its inverse, add inverse. That's the resistance at this point. And let's store alpha B. Again, not necessary, but if you ever want to go back, like you make a mistake, I can just pick up this answer. Keep on going. Now in series with J200, 0, enter 200, complex. In series, they add. And parallel, take the inverse, 0, enter negative 500, take its inverse, add the inverses, plus 100. So it should be 212 minus J151. And that checks. Next problem. You can kind of see how the HPs are such nice calculators. This is a typical test problem you're going to see in circuits 1 towards the end. but you need a calculator that can add complex numbers in series, parallel. HBs do that. So start out, I've got J400, and parallel with 400, add the inverses, so all this together is 200 plus J200. In series with 30, so at this point, let's store that in A. I've got 230 plus J200. And parallel, take the inverse, in parallel with minus J200, 0, enter, negative 200, take that inverse, add, 300, take its inverse, add, so that's all three of those in parallel, take the inverse, that's 138 minus J168. So at point B, let's store that number, plus 60, so there's your answer, 198 minus J68. Okay, so that was the first two problems. The next set of problems is voltage nodes. If you don't mind complex numbers, AC analysis is just like DC analysis, except I have complex numbers. For example, if I have this circuit and the input is DC, 10, solve. Well, we've already done that. The capacitors don't matter. The impedance of a capacitor is 1 over j omega c, or infinity. Or another way of looking at it is the current is C dV dt. If the voltage is constant, dV dt is 0. So this current is 0, meaning ignore it. This current is 0, ignore it. This current is 0, ignore it. You can basically ignore capacitors at DC. Now, write your node equations. The mathematical representation of 10 volts is the number 10, not surprisingly. So my first equation is V0 equals 10. At V1, the current left, current down, current right equals 0. That'll be V1 minus V0 over 2, plus V1 over 300, plus V1 minus V2 over 2 equals 0. Likewise at node 2, node 3, node 4. Again, to check your answers, all the V1s are positive at node 1, everyone else is negative. All the V2s are positive at node 2, everyone else is negative. And I have amps plus amps plus amps. The units all match up. To solve, I group the terms, put it in matrix form. So for example, this equation, let's call this is times V0, V1, V2, V3. This equation is minus 1/2 V0, plus this mess times V1, minus 1/2 V2 equals 0. Put that in MATLAB and solve. So this gets kind of unwieldy. So I actually did the first row, second row, third row, fourth row, put it all together. Here's my B matrix. And the voltage is inverse of A times B. To check, I can build that in Circuit Lab, do DC solver and solve, and I get exactly the same answer. So that's DC analysis. We've already done that. Now, let's change the problem. Suppose the input is 10 sine 2000t. Now solve. This is where you use phasors. In phasors, the voltage is, the real part is cosine, minus j is sine. So my input is minus j10. It's 10 volts as a sine wave. 0 volts is a cosine. The resistors stay the same. The capacitor becomes 1 over j omega c. Omega is 2000. C is 30 microfarads. So if I try that, I've got omega is 2000. C is 30 microfarads times j. So there's 1 over j omega c. Take the inverse. This is minus j 16.67 ohms. 40 microfarads, 50 microfarads, you get a complex number. This is unwieldy to do with the calculator, so this is where we use MATLAB and matrices. I know that V0 is minus j10. I know at V1, the current left, current down, current right. plus one more term, plus this current equals 0. That's your V1 minus V0 over 2, plus V1 over 300, plus V1 minus V2 over 2, same as before, but now add a term, plus V1 over minus J16.67 equals 0. Likewise at node 2, likewise at node 3. So when I write my equations, it's exactly the same as before, but I now have one extra term. That's the voltage through the capacitor, and my input. It could be a complex number. Real part means cosine, minus J means sine. In this case, it's a sine wave. 4 equations, 4 unknowns, group the terms, throw into MATLAB. Again, exactly the same as we did before. I just have that one extra term. Throw in MATLAB. So again, this guy is kind of different. Let's do a highlighter. So this is what's different between AC and DC. That's not a highlighter. There's a highlighter. This guy's the difference between AC and DC. Add that one extra term. I now have a sine wave. And a little bit different here. My input is minus J10 rather than just 10. Make those differences and solve. And that's my answer. Real part is cosine, minus J is sine. So if I want to represent that as sines and cosines, I just take each term. 0 cosine, 10 sine, minus 2.72 cosine, plus 7.73 sine, minus 4.53 cosine, plus 5.84 sine. There's my answers. Now to check my answer, that's rectangular form. Polar form is actually easier to use. If you take the magnitude of voltage, the absolute value, that's the peak of the sine waves. When you go into lab or use circuit lab, the peak, that's the magnitude. Take the absolute value of V, that gives you this number. And so again, do this, do a sine wave, 10 volts. To get the answer, I can't do a DC solver. I kind of have to do a time domain simulation just because the voltages are changing. What I like doing is one period, let's do it this way. It's 2,000 radians per second divided by 2 pi. It's 318 hertz. Take the inverse. The period is 3 milliseconds. So let's plot this for a couple cycles, say 3 cycles, 10 milliseconds. And make the step size 1,000 times smaller, 10 microseconds. And what you get is a graph like this. That's got 1,000 points on the plot. Take one of the later ones. I got the starting transient, here's steady state. But we're calculating a steady state. Find these voltages. And you can do that in Circuit Lab just by moving the cursor, and it'll tell you what the peak is. When I did that, here's the peak that I got. Here's what I calculated, and the two should match. Now with complex numbers, there's also an angle. The angle is this delay. So a cosine is the peak right here. The sine wave is delayed by that much. The next waveform is delayed by a different amount. That's polar form. In polar form, I get the amplitude and the delay. Delays in degrees. I usually just use amplitude. If you got the amplitude right, it's probably the right waveform. But the math will tell you both parts. So that's homework set number 9 for ECE 111. The point being, if you don't mind complex numbers, AC is just like DC. In electrical computer engineering, we kind of live and breathe complex numbers. The reason being, anytime you deal with AC circuits, I'm stuck using complex numbers. So we live and breathe complex numbers. And likewise, you need a calculator that works with complex numbers. I highly recommend the HP42. It is just a beautiful calculator, in my opinion, best calculator ever built. And it's a free app on your cell phone. So get used to it. I highly recommend getting used to it. When you get to circuits, you're going to need a calculator that does complex numbers. Learn how to use it now. Don't learn how to use it on a test, because it is a little bit odd. It's got a learning curve. Once you figure it out, it's fast. HPs will dust anyone else. But that's homework set number 9.